Good morning. So let's again start. Today we'll study two topics, rather three topics: authenticated encryption, pseudo random number, and SIM ciphers. So I will be going a little fast because note that we are still in crypto topic, right? Okay, and we are not going into great details, proofs, etc., because it requires a lot of understanding of mathematics. I mean, they're all based on mathematics, and we don't have time if we want to cover other topics because you know we the more course is designed more towards system side, okay, or something that can be applied rather than uh, basically a crypto side. Okay, so if you want to learn more about crypto, a lot of good books and video tutorials are available. I can send you the links. Okay, but we still want to cover all concepts of cryptology. Okay, that's useful to us in something that we'll study next, that is network security or internet security. So these are the references that I have used. Okay. All right, so this is where we are in cryptography roadmap. So we have completed one-time pad, block ciphers, like Semitic ciphers like EBC, CBC, CTR, etc. Then that was for confidentiality. For integrity and authentication, we have studied MAX, and of course before that we have studied hash functions. Okay, this part we have to do, and this also, like digital signature, etc., we will study later on. Okay, so today we'll study this one. Okay, and of course authenticated encryption. Okay, all right. Before that, let's see what we have done so far. So that will give us motivation to learn more things, right? Because what we have learned so far may not be sufficient for to provide security on internet. Okay, so this is what we have studied: symmetric encryption. We have looked at various blocks, cipher schemes like EBC, CBC, CTR, etc. And we have seen it works beautifully, and most of the system today, practical system, use this because it is very fast. Okay, it provides confidentiality because key is shared between the two entities. Only these two entities know the key, hence is confidential. Okay, but encryption is secure only against eavesdropping, means like a person like Eve who can see what's happening but cannot do man in the middle attack. So man, if there is a concept of man in the middle attack, the man in the middle will intercept the traffic or intercept the message and can change the message and send it to Bob and so on. Okay, so but this is not safe against man in the middle attack, right? So integrity is no. So if instead of Eve, if Mallory changes something here, Bob will not be able to detect it, right? Authentication, of course, no. Okay, non-repudiation. We have not discussed these terms too much so far. Non-repudiation means that if Alice has sent something to Bob, later on Alice cannot claim that she has not sent anything. Okay, or she cannot refuse a transaction she has done. Okay, that's called non-repudiation. So non-repudiation here, is it possible? No, because it's based on symmetric encryption. So if Bob says I have not received anything, okay, Alice has sent something and Bob says I have not, then nobody can prove that, or court cannot prove that Bob has not received anything. Okay, all right. Or Alice says that I owe you $100, and Bob says that I have received a message which says that she owes me $10,000, right? This cannot be proved because it's based on the trust between the two entities, Alice and Bob, and both use the same key. but it's not safe against the two parties who can cheat each other. All right. Second thing we studied was cryptographic hash function. Okay, which basically take a message and by compression and very intelligent way we get a hash of fixed size. So if we send a message and the hash to other party, confidentiality no, because message is in plain. Integrity, it depends on threat model. If the hash value is not changed in the transit, then of course yes, otherwise no. And then non-repetition no. So if it is so, then why is it used? That you have to answer. Because it's very interesting, very good primitive, but it's used along with others. Hash in just plain form can be used, of course, and we have seen one example and exercise that I've given to you, right? But in general, it is used with other cryptographic primitives or cryptographic functions. Okay, then we have studied MAX, message authentication code, wherein we, what we do is that we use the symmetric tree method and then send a tag along with message, and that is based on the key. Now note that key at both ends is the same, but it may or may not use encryption method, because if you use encryption method, if using this key and MAC function is just plain encryption, the size of the tag will be as big as that of a message, and we don't want that, and it's also very time consuming. Encryption in general takes more time than hashing. Okay, so now we have designed some MAC functions. Okay, then what we get from this is confidentiality no, because message is in plain. Integrity yes, because this T is a message is tempered by mallory in between. It will be detected at the end, because this guy Bob knows the key and will decrypt it and find out that tag doesn't match, right? Okay, and if Bob changes both message and tag, even then Bob can find it out, because only Bob and Alice having the key. So when Bob will decrypt it, whatever corrupted message he has received will calculate the tag, and that tag cannot match with the tag generated by Mallory, because Mallory doesn't know the key. Okay, so integrity is yes, authenticity is also yes, because now key is known only to Alice and Bob, so it's sure that whatever is received by Bob comes from Alice. Okay, all right. Non-repetition, no. Okay, because again it's based on symmetric encryption, and Alice or Bob cheats, then there's no way in the system to find out that there is a cheating. All right, you got it? Any question? All right. So one example of MAC is that we can protect system files. So okay, all right. You have a laptop, you have files, okay, and these are all system files. I mean, system files are files that are used by OS. Okay. Okay, now you cannot do this for all. If you want, you can of course do this for all the files that you have, but you will have 10,000 files, may not be required. Okay, so you take all these files, okay, system files, and use the key K that is derived from your password. Okay, and then what you do is that you get MAC, use a MAC function, okay, and get a tag. Okay, now let's assume that your system gets corrupted. Okay, I mean there's an attack of virus, and what do? Then you boot your system with fresh OS, right, or clean OS. That's the only thing that you can do if your OS or system files are corrupted. Okay, now then you supply your password. Okay, from the password it can generate key. Now what we'll do is that it will get the max of all the files, system files, and then compare it with the tag that's available. Okay, now if system file is changed, it can find it out, and if the system file and tag both are changed, even then it can find it out, right? So from this system can find out all the files that are corrupted, because again we are using some, let's say the file is corrupted, then MAC of this key is the same, that's not known to virus, right? So what you will do is that you calculate tag. Now if you have clean tag available, match it, and you find this it does not match, then you know that file is corrupted, right? Okay, now if tag is also changed by a virus, then obviously chances that that tag will be same as the tag that's generated by the key using this method is very, very less, because MAC uses a single bit change, makes huge change in the output, and also it has to done exhaustively, right? Because as we have seen, it has to generate all possible combination for these two tags to match. So it's not possibility. So hence the corrupted files can be detected by this method. Any question? Yes or no? Okay. Look at the reference. This I have taken this from slides by Professor Dan. He has a beautiful online tutorial available in YouTube. Or you go to Stanford site and you'll find all his talks. It's beautifully done. If you want to really understand crypto, then all video lectures are available and you can go through them. All right. So what we achieved so far? We have achieved confidentiality and all, in some sense, separately integrity. But we want to see, the whole idea is that we want to achieve confidentiality plus integrity plus authentication. Now integrity, in most of the users will include these two under term integrity. All right, but technically these are different. Okay, so integrity, here I am talking integrity, and also we want non-repudiation. So all this we want to achieve, and we have achieved this in bits and pieces, right? The scheme that is confidential may not be may provide integrity, and a scheme that is confidential in that provides integrity cannot provide confidentiality, and so on. So we want to achieve this. So let's make another attempt, and something, this method is called authenticated encryption. Okay. All right. So we want to achieve these three. Okay. Now, not necessarily that everything that we are, this will be, all this property will be achieved, or this scheme will all be under all cases, right? All test cases or all use cases, right? So sometimes there are limitations. So we cannot say for all kinds of attacks, all these schemes, this scheme will provide confidential authenticity everywhere, right? So there are some cases where this may fail, but in general we can say authenticated encryption scheme provides these three, based on, of course, some threat model, but we assume that threat model is not very, very difficult threat model. Okay, so the three approaches we'll look at. First is encrypt and MAC, second is encrypt then MAC. Note the word then. First encrypt and then MAC. Third scheme is in MAC then encrypt. Okay, first you do MAC and then the encryption. Are you able to understand something out of it? Okay, let's look at it. See, now we have not tried to combine these methods. We have seen symmetric encryption method, we have seen also hashing, we have also seen okay, what else, right? MAC, and we never try to combine them. Now we can combine these methods and see, can we get all three properties, that's confidentiality, integrity, and what was the third one? Authenticity. Okay, now the word C in CIA, there's a model CIA is usually used for availability, but here what we want to achieve is authenticity. Availability is more of a reliability concept and availability concept, wherein system should remain available despite having all kinds of threats. So we'll not study that in this class. Okay, the first is approach is encrypt and MAC. And word, note the word and, right? So you have message M, you encrypt it using a key K1. Now note that this key is symmetric key that's shared with end user. Like Alice and Bob shared that. Okay, so what we get is ciphertext C. Okay, and take message M and get MAC from that. Okay, the MAC is a small, is like a tag, but that also note that MAC is also based on symmetric key concept. So it will use different key. The key for encryption is K1 and key for creating MAC is K2. Okay, so now this is sent to other end. So it will have some properties now. Okay, now we can see there is a confidentiality, assuming that you are using proper block cipher mode. Okay, and it will also have integrity, because something has gone bad, then you can find it out through MAC. Okay, all right. Okay, all right. So now what is the issue here? So note that we are using two keys, K1 and so K1 and K2. K1 for encryption decryption, and the K2 is a MAC key. So so we can see confidential integrity, but integrity is fine, but confidentiality is not. So MAC here is not IND CPA secure, right? From this, Mallory can find out some information just by tricking Alice in repeatedly sending MAC of the message, right? So we have seen that MAC is not IND CPA secure, so it will leak some info. So this scheme can be used, and it is being used in many protocols. Okay, but it is not 100% secure, or this method is not 100% confidential, because MAC in many cases may leak some information. Okay, we are not going to proof of this, but just try to understand. This is based on whatever we studied so far. Second scheme is called encrypt then MAC. Okay, it's obviously we are encrypting first and then doing MAC of that encrypted message. Okay, all right, so it will look something like this. Okay, take the message M. Okay, encrypt this with key K1. Okay, and take this whole ciphertext. Okay, and on this ciphertext you do MAC. So you do MAC of K2 on this becomes the content on which you are trying to get MAC. So this is what comes here. So now to other party, that is if Alice is generating all this, Alice is sending to Bob C and MAC of okay C with the key K2. This is being sent as a message, right? So message or the something or packet that is being sent, or the message that's being sent, you'll have two parts. One is ciphertext and concatenated with MAC. Okay. Now this scheme is the best scheme that is proven to be, because it provides integrity because of the MAC. Okay. Note that now MAC is that of a ciphertext. All right. So now we can say that is secure, but again MAC, is not CPA, IND CPA secure. So it will leak some information about this encrypted text or ciphertext, which is okay in most of the cases. Okay. All right. Now third scheme, any question? All right, I'll go ahead. Third scheme is called MAC then encrypt. What are we doing? First, take a message, just MAC of that, and then concatenate both and then encrypt. Okay. So it's like this. You take a message M, okay, and use MAC algorithm that you studied, okay, and take M as a now you need to find MAC on message M using key K1, K2 on message M. Is shown is this one, as this one, right? So MAC, get the MAC or tag of this message, okay, using K2 key on M, and then what you do is just concatenate both, and then take this as a message, okay, and then encrypt this using key1, key K1, right? So take this message and use encryption function, whatever encryption we have, you want to AES, CBC or whatever, right? And then you take this whole as contained and use key K1, and this becomes M dash, and that whole text comes here. It is now being sent to Bob. Now the question you may ask, how Bob will come to know what is MAC? It has to somehow find out MAC portion, this portion, okay, and ciphertext, right? So now these are the part of protocols that we are not going to study now. Okay. And if Mallory is doing man in the middle attack, and she is able to corrupt this C, and we know that there is nothing goes here along with C, right? Now the protocol will require first this to decrypt, okay, and then check whether it has been corrupted or not. So it's a little complicated process. Okay. All right. So now these two methods that we studied is shown again described here. We'll skip this. Okay. So now encrypt then MAC, that this method. Okay. Encrypt this then MAC. Okay. All right. This method is preferred method. Okay. All right. So this is preferred method because the more robust to mistakes. Okay. So MAC then encrypt is also being used, but it has some problems, right? Because first you need to decrypt and so on, right? And there are some attacks called side channel attacks that are possible. Now we will study side channel attacks little later. We'll just look at what side channels attacks are. We'll not go into great details. Okay, but when we study attacks, then we'll look at these, right? And also improper use of cryptographic schemes cause some information to leak, like completion time, error message, return, etc. So note that when you are encrypting and it's taking some time. Okay, if somebody is watching just how much time you have taken and what is the error message you have received, etc., and all these are visible to third party, then we say that is kind of side channel attacks, right? Somebody is looking at you typing your password and can guess what fingers you have pressed from a distance, right? So this is not normal way of attacks, right? So this kind of attacks by some collection of some parameter, observing some parameters, are called side channel attacks. So MAC then encrypt is vulnerable to side channel attacks, right? Okay, so we'll not get into all that because whole idea is that to tell you that what are different methods. Okay, now one thing very important is that use different keys for encryption and MAC. So we have seen we are combining two schemes. First is encryption and second is MAC. Okay, so in three different ways. Okay, so now encryption is symmetric encryption, so it will require a key. MAC also based in a symmetric concept. Okay, and of course we use hash function inside, but it also uses a key. Okay, now these two keys have to be different, otherwise it will not be secure, right? Again, there is a proof available for that. So how to choose key1 and k2? That one has to find out, right? I mean, a best is that you can generate a random key or pseudo random keys or whatever. Okay, all right. Now, are we using authenticated encryption scheme? Yes. Like you would have heard about SSL, IPsec, and SSH protocol, right? All these are used in internet. Okay, so MAC then encrypt is used in SSL. We can take message M, then do find MAC of that, and send this as a. Oh, I'm sorry. MAC then encrypt. Okay, sorry. So first you get MAC and then encrypt everything and send this as a all encrypted message. Okay. So this is used in SSL. Then second is encrypt then MAC. First you encrypt this message and then get MAC of this encrypted one. So MAC of this and then concatenate both and then send. And then third is encrypt and MAC. Take message M, get encryption and get MAC and attach tag to encrypted one and send. And that's being used in SSH. All right. Okay. So this is the one that's always correct. Encrypt then MAC. All right. Any question? Are we going fast? Hello.
No, no, sir.
Okay. Okay, all right. So now we have completed this authenticated encryption. What we have achieved? We have achieved confidentiality, integrity, and authentication. All right. Now the question now I am asking you that can as it is we can do this. Okay, look at your IP protocol or IP packet. There is something called header and then something called payload. Payload contains the content, right, or other packet. The IP packet may contain inside a TCP packet. Okay, TCP packet will also have some header and then some contents, and TCP packet may internally contain some data. Okay, so the actual useful thing is the data, and then rest of things are headers, right? Okay, now all right. So now forget about TCP. Just look at IP address, IP packet. IP packet header will have some information, like you receive a packet at home. You know, your parents will send you sweet. Okay, and then it will have to have certain things, right, for packet to reach you. What is minimum thing that is required for packet to reach you? Inside could be anything. It could be laddu, barfi, whatever you want to eat. Your mother will make and send it to you. But for packet to reach, you need some address, right? Your address, and this address has to be unique. Okay, so any packet that goes on internet will also have destination IP address. And also will have source IP address. Who is sending? Like your parents will say is sent by, you know, whatever, your father, and the address. Okay, and then it will have some more information. Your you know, father may write urgent, or may say write something about, you know, the fragile or whatever. Okay, anyway, so there can be some other fields, right? So the important thing is source and destination address, and destination address is the most important. Without this, until your name and address written, it cannot reach, right? So now, if this is the packet that is being sent on internet, what all can be encrypted? Now, can you encrypt the whole packet, including your name, or including IP, destination IP address? No, it cannot be, because, you know, in between there are routers. How will they know? Like, you know, if your address is, there's some tape is put on top of your address, name and address, then postman in between, or, you know, post officer in between cannot find out where that is. Similarly, so IP address, at least a part of the header, has to remain in plain text. That's the crux of the story. Okay, so the encryption for this we call AEAD. Okay, so it's called authentic encryption with additional data. That additional data that it has cannot be encrypted, but we can provide integrity. So this is a method to provide confidential and integrity to, say for example, something like IP packet, where for certain part you can provide only integrity, but for rest of this can be encrypted. All right, okay, that's the concept. Okay, all right, so now there are methods available for this one. Okay, so and we'll study some protocol, like IPsec is one such protocol. Okay, so all right, so we'll not get into great details, but we just wanted to mention this. So I had, sorry, eight AEAD provides confidential, like block cipher most, and integrity and authenticity. Okay, so integrity is provided by additional message and additional unencrypted data, like name and address and IP address, etc., especially source address. Okay, so for example, as I mentioned you, if Alice wants to send a message to Bob, and she wants to write here from Alice to Bob on top of envelope in plain text, okay, then system should allow that something she has written should not be encrypted. Okay, should be visible, but Mallory in between. If Mallory changes this to Mallory to Bob with love, this should not be allowed. If she does that, it should be detected. So it means that there has to be integrity. All right. Okay. So basic idea is that it's not always possible in systems or protocols for packets to encrypt everything. So there should be methods available, okay, such that part of that packet can be encrypted, like here, this encrypted part, and then something that needs to go in plain that we call associated data has to be authenticated. It means that if some changes here, then it should be visible, and everything should then be authenticated. Okay, that's the concept. So again, when we'll study internet, we want to have three main goals, right? Data privacy. Okay, it means the data should not be visible to anybody else, or we can call it confidentiality here. Data integrity, or mallory should not be able to change, and data authenticity. It means that if message is coming from Alice, actually it is coming from Alice. All right. So these three things we want to achieve. These are the goals, and we are still working towards these goals. Okay. Another 15 minutes, 10 minutes. We'll study was pseudo random number generator. Of course, we'll not get enough time to complete this. Okay, what is the need for pseudo random number generator? And you would have come across this term very often.
Sir,
Okay, why do, yeah.
sir, how Bob will get to know that additional data has been changed?
Okay. Additional data has been changed because of we are providing integrity over that. We are not looked at the whole concept, right? We are just give what, how do we achieve integrity?
Sir,
We
sir,
have studied, right? By
integrity
MAC.
has been lost now if associated data has been changed and Bob will not get to know.
Oh, okay. We are not studied the full protocol as yet, right? This is just to illustrate you the concept. We have not looked at associated data, what is whether we are using MAC or what, and then it will be attached at the end, and a lot of other things, right? Of course, if what do you say that if some this is lost, right? What is your
Yes,
question?
sir. Yes, sir. If
Then nothing
associated
can be
data
done.
has been, yes, sir.
Yeah, nothing can be done. I mean, if your packet is dropped by router in between, then if you are using TCP, then it will take care of it, right? Packet will be sent again. But if packet reaches other end, then how Bob should be able to find out, whether it has been changed? It can be done only by integrity, right? You use method like MAC, etc.
Okay, we are attaching
Okay.
Mac with the,
How you, of course, this is just to illustrate concept. We are not sending this as it is this, but there has to be, when you study IPsec and other protocols, we'll see what are the parts of it, right? In fact, if you look at this, I don't know, yeah, you can see that it has some integrity check value and all that, right? So that will go also as a part of the whole packet.
so basically why we are using this plain text, not an encrypted one in associated data?
Yeah, exactly same thing that I have explained. Like your mother sends you a packet of laddu, and she will put that inside a box, and on that your name and address is there. Okay, now encryption means that a sticker that contains your name address is changed. You put another sticker of black color, she puts another sticker of black color or whatever, or she has something, she creates some pattern here. That's the encryption of your name and address.
Yes, okay, okay, got it now. Yes,
Okay, then how postman in between will know it's coming to you? So router in between, if IP address also encrypted, until router has that key,
yes,
decryption key, will never come to 9. Why should any router in between have the key for decryption? Right?
yes, I
Because
got it.
purpose of encryption or security is that two end parties should have something it should achieve property of confidential. The router in between then have the key, then can decrypt everything. So the point I am making is that something in a protocol cannot be, or packet cannot be encrypted, because it's being used by intermittent or intermediate routers or sources, right? And that, but we need to still protect it, right, such that Mallory does not change. See, Mallory receives in between and changes that these laddus are for her, not for you. Then of course she will receive it and enjoy it. Okay, now somehow, okay, all right, so she should not be able to, if she changes something, then you should be able to know about it. So that, so what you'll do, this part can at least be, we can provide integrity of this, right? A recipient will know that something has changed. All right, got it?
Yes, sir.
Okay, all right. Okay, so question is that why do we need random number? So we have used random number so far, right? Where did we use it? Where did we use? See, in life we use randomness very much, right? So even something that you studied, we have used random numbers.
in the
We
key
have used
generation.
so far in the protocols, right? We have used IV concept, nonce. We have used these concepts, right? And the keys. If you generate key as, you know, say that 0001, 0002, and whatever, you know, this could be say 128, 000 is a 128 bit key, one starting from 0001 to whatever, everyone can guess it, right? So when we generate keys, they have to be randomly generated, like, you know, in symmetric encryption, the key that you are generating has to be randomness into it such that nobody should be able to guess it. That's a random number generator. Then we have used IVs, initial vectors, okay, in CBC mode, etc. That also has to be random. Nonces are random. Okay, so in crypto, did you try to understand how Bitcoin works? Bitcoin, you know, how do you withdraw money, or how do you do transaction? For every transaction, you create your own key, and this key is generated by you, okay, among millions of keys. The key space is very big, okay, and that key you generate, the probability of that anybody, so you, by generation of that key, you can claim the Bitcoins, right? But probability that anybody else can generate that key has to be very, very, very small, because everyone is generating keys randomly. So random number is used very, very often in cryptography. Okay, and the application, like your Linux machine or your Mac OS machine or Windows machine, will have pseudo random number generator. Okay, and randomness plays a lot of role in our life. Okay, because world is fundamentally random according to a theory. Of course, I don't believe it 100%. Okay, but events in our lives are often random, and I'm going to a market and can meet with an accident. Of course, I am driving properly, but somebody from front can come and hit me, or I'm going and somebody, you know, something can fall on me. So these are all random events. Okay, and if you're not read this book, this is a classical book, please read this. You know, Fooled by Randomness. Something happen in our life and we think I am great. You know, if something is, for example, I made say $100 in my, I bought a stock and tomorrow it becomes, you know, 50% more. I think that I'm really smart guy. And then, you know, it happened just by chance that that company somehow clicked. Something happened to that company, but not necessarily the company is great. And then if I do the same thing, then sometime or other I will start failing. Okay, so this is a nice book. Please go through it. So these three we have already studied. Also, when we want to create universally unique identifier, all user IDs that we create, right, has to be universally unique for that system. Okay, and of course they allow us to have user ID which sounds like our name, but many banks have just account numbers. Okay, or something like that, which are universally unique identifiers. Or the your password manager may create a password, will your password will create a password, password manager will create password which looks like a random. Okay, and if an attacker can predict random number, then cryptography will fail. Whatever encryption you are doing, keys are generated randomly in symmetric key encryption. If this can be guessed, then game is over. Okay, the question is that then how do you generate random numbers? Note that, please note that everything that we do in computer is deterministic. You write an algorithm to create a random number. How can you create? You say from 1 to 50 do add, multiply, subtract, all that, and you can have some logic in between, conditional logics, etc. But ultimately, every run of the program will get the same answer. That's how computers are designed. All what do you do in computer? You say that do this one thing, second thing, third thing. If you have this data, then do something else, and it changes the program execution direction based on the data, and then finally something is some output comes, but all inputs to this program remains the same, then you get the same output. Is that right? Then in computer, how do you generate a random number? That's the question. What is random, for example, in life? What is the temperature of my laptop now is kind of random. If I measure it, with 3 digit, or maybe, with high accuracy. Okay. What is the volume of my voice? Could be random. Okay. At some instant taken. Okay. So there are a lot of things are random, but taking my voice input and getting a sample from that and encoding is all very expensive. Okay, so we need to create a system such that we use these actual random events which are very expensive and then create random number which we call pseudo random number, because they are generated from true random numbers. Okay, by introducing some randomness, to randomness. So to take some two randomness, generate set of pseudo random number, and then after some time again introduce some randomness, to randomness, and generate set of pseudo random number, and so on. Okay, two random number is a flipping of a coin, right? Suppose you want to every coin flip is a fair coin, and then 50% probability, and generate a sequence of n bits, and then just 100% random, right? But you can't do that in system, right? Okay, how do you generate a random flipping? How can you simulate flipping of a coin on a on your program, right? Okay, again you need some randomness to do that. So entropy is called measurement, a measure of uncertainty. Basically it says that is a measure of how unpredictable the outcome becomes. Higher the entropy, higher the more unpredictable outcomes are, right? Okay, so we need higher entropy sources in cryptography. All right, so then we have to have true random number generator, which of course we can, best is of course flipping of coin for 100 times, but that is not possible. Okay, so we take some sources like an unpredictable circuit in CPU, so how much heat the circuit is generating, or something else, or human activity measured in very fine time scales, in microseconds, etc., etc., of a movement of my hand, fingers, or flipping of eyebrows or whatever. Okay, or semiconductor noises and clock jitters in digital circuits. Those these can give you true randomness if measured properly. Okay, and from that we can generate pseudo random number, because two random numbers, generation of two random is expensive and very slow. Then we, from this we generate pseudo random numbers, which we call it PRNGs. Okay, so now in next class we'll study what are the methods, right? We take the seed, which is two random numbers and random number, and from that you write a program. This will generate pseudo random numbers, okay, which looks seemingly random for an out for Eve. If suppose Eve sees this random number, she will find that these are actually, for her it will look like random. But now note, any programming that you do is all deterministic. It's the same program you run 10 times, you get the same answer, right? So you have now, this program logic has to be intelligent enough such that from true random number, which is seed, you generate sequence of bits which looks like random. That's it. That's the game. And then there are properties and mechanisms for that and so on, right? So we'll look at some of these properties in the next class. All right, and we'll look at one such algorithm for that in the next class. Okay, all right, and then we'll look at steam ciphers. All right, so that's all for today. Any question? Okay then, thank you.